video, we're going over some GCSE physics problems about circular motion. Just to recap some of the equations that are needed before we look at some example questions. Objects travelling in a circular motion are prevented from moving off in a straight line by centripetal force. This resultant force pulls objects towards the centre of the circle, continually changing the direction that an object is travelling to keep it in a circular motion. A larger force is needed if the speed is increased, the radius of the circle is decreased, or the mass of the object is increased. F, which is the centripetal force, is equal to the mv squared, m being the mass, v is the linear velocity, and r is the radius of the circle. Angular displacement measured in degrees or radians. Theta equals d divided by r. Angular velocity equals omega equals theta divided by t. Therefore, omega is d divided by rt. Omega r equals d over t. So v, the linear velocity, equals the angular velocity multiplied by the radius. V equals r omega. Question 1. A motorbike is being driven around a circular bend in a road. AI. In which direction does the centripetal force act? It acts towards the centre of the circle. A2. What provides the centripetal force on the motorbike? Friction between the road and tyres. What happens to the centripetal force if the motorbike is driven around the bend at a higher speed? The centripetal force increases because F is proportional to the square of V squared. What happens to centripetal force if the motorbike is driven at the same speed around a bend with smaller radius? So if it's the same speed but it's got a smaller radius, then the centripetal force is increased because force is proportional to 1 over r. So as r decreases, F increases. Question 2. The diagram shows two children playing with a toy called a swing ball. The ball is joined to a pole by a strong string. The children hit the ball so that it goes round in a circular path. So the tension acts inwards, producing the centripetal force. Choose the correct response. The force needed to make the ball move in a circular path is larger if the speed of the ball is increased. F is proportional to v squared. The continuous acceleration of a ball moving in a circular path changes the direction of the ball. The acceleration is in towards the centre of the circle. A student has fastened a ball to a piece of string and is swinging it around in a horizontal circle. The diagram above shows an overhead view of the movement of the ball. So you've got the linear velocity tangential at any one particular moment to the circle. Complete the diagram by adding an arrow, and this is how it's done. Okay, to show the direction in which the ball would move if string broke at this instant. 4. A ball of mass 100 grams is fixed to a string. It's being whirled round in a circle of radius 40 centimeters at constant speed. Find the speed of the ball if the force tugging on the string is 2 newtons. F equals mv squared over r. Therefore, phi equals the square root of fr over m. That's rearranging this equation. So formula, rearrange, substitute. We substitute in the values for F 2, R 0.4 because we have to have that in meters. So 40 centimeters divided by 100 is 0.4 meters. 0.1 comes from the mass needing to be in kilograms, so we divide through by 1,000. So 100 divided by 1,000 is 0.1. Gives our answer of 2.8, and the unit is meters per second. Question 5. A space station has a radius of 100 meters and is rotated with an angular velocity of 0.3 radians per second. So this is the angular velocity, 0.3 radians per second. Which side of a room is at the rim is the floor? Which side of a room at the rim is the floor? So if it's going this way, then what that's going to do is it's moving around the circle like this. Oops. like this, or around the circle, like this, anti-clockwise as we're looking at it. And so the centripetal force is going towards the circle, and what that would do is it would produce a reaction outwards, and so it would feel as though this side is the floor, because this side here would be pushing against. It'd be like an apparent force called a centrifugal force. It doesn't actually exist, but this floor here would be pushing towards the person standing in the space station. What is the artificial gravity produced at the rim? So this is what we call artificial gravity, right? It's the apparent force which is opposing the centripetal force. Acceleration equals v squared over r equals omega squared r squared divided by r equals omega squared r. Simplifying, omega is 0.3, so we square that, multiplied by 100, 9.0 meters per second squared. So a bit less than the gravity on the Earth. Remember, gravity is just an acceleration. The wire is 1.5 meters long and has a mass of 7.5 kilograms fixed to its end and can withstand a maximum tension of 1000 newtons. What is the maximum angular velocity and period of rotation with which the wire and mass can be spun round in a horizontal circle without the wire snapping? So we've got to use m equals v squared over r, f equals mv squared over r equals m omega squared r squared divided by r, which is equal to m omega squared r. Therefore, omega, rearranging, equals the square root of f divided by mr equals the square root of 1000 divided by 7.5 times 1.5 gives 9.4 radians per second. Using v equals that speed equals distance over time, constant speed, 2 pi over r divided by t, therefore the period of rotation equals 2 pi r divided by v, which is 2 pi r divided by omega r, which simplifies to 2 pi divided by omega. 2 pi is a constant, we know what our omega is, so that we know that we can find the time period of 0.67 seconds. Calculate the rate of rotation for a space station of radius 65 meters so that astronauts at the outer edge experience artificial gravity equal to 9.8 meters per second. A equals v squared over r, therefore v equals the square root of ar equals the square root of 9.8 times 65 equals 25.2 meters per second at the outer edge. Or a equals omega squared r, omega squared equals a over r, omega equals square root of a over r equals the square root of 9.8 divided by 65 equals 0.39 radians per second. Space station should have an angular velocity of this, and it should have a linear velocity of this.